Here we're asked to simplify the expression and write it as a single radical. In other words, for the most part, we're being asked to add and subtract radicals. Key to adding radicals is identifying like radicals. That's very much like identifying like terms. For example, if instead of 2 root 7 minus 5 root 7 plus root 7, we had 2x minus 5x plus x, we'd know exactly what to do. We have three terms. They're like terms because they're the same letters raised to the same exponents. So we simply do the addition and subtraction of the coefficients. So we have 2 minus 5 plus 1. And our answer is negative 2x. We do the same thing here. Rather than like terms, we call these like radicals. They have the same radicand, so the same number under the radical sign, and the radicals are all the same order. They're all square roots. So, much like the x's, we simply take 2, subtract 5, and add 1. So we have negative 2 times the square root of 7. Essentially, what you can think of doing here is replacing all of the like radicals, here the root 7's by x's, actually doing the addition and subtraction of those algebraic expressions, and then returning the square root of 7 in place of the x. That's more complicated than it needs to be, but that's the idea. We'll do this again with the example on the right, 3 root 2 plus root 8. As this expression is written, we can't actually add the radicals. They're not like radicals. They're both square roots, but they have different numbers under the radical sign. So we should check if we can simplify any of these radicals. Square root of 2 can't be simplified. It's already a prime number, in fact, but the square root of 8 certainly can. So we have 3 root 2, and we can rewrite the square root of 8 as 4 times 2. So that gives us 3 times the square root of 2 plus the square root of 4 is 2, so plus 2 root 2. And now it happens that we do have like radicals. 3 root 2 plus 2 root 2 is 5 root 2. Now notice that when I went to simplify the square root of 8, I wasn't focused on getting the square root of 2 to remain behind. I simply simplified the radical, and it was convenient, it was handy, that we ended up with the square root of 2 and like radicals. It's possible that when we simplify here, that we still end up with 2 unlike radicals, and we simply have to leave the expression as is. This one just worked out really nicely. This last example here reminds us how the order of operations works. So there's no rule, remember, for adding underneath the radical. What we just did, square root of 2 times the square root of 4, turning into root 4 times root 2, that works because we have a product. It would also work for a quotient. But if we had 4 plus 2, that's not at all equivalent to the square root of 4 plus the square root of 2. So that can't happen. Think of it this way. If it's under the radical sign, you can rewrite that so that it is a set of brackets raised to an exponent. So we have 100 plus 25 in the brackets raised to the power of a half. I think we're more familiar with the exponent notation and notice immediately that we're going to have to add what's inside those brackets first. Same thing for the example down here. The only thing we could do is take the 4 and the 2 and add it to give 6. Same thing here. All right, so we'll take 125 and add them together. They're still not like radicals, but at least we're ready to go. We're at the stage where we can at least consider simplifying the radicals. The square root of 125 simplifies nicely because 25 times 5 is 125. Let's simplify the square root of 80. Again, one way to do this is to draw a factor tree if it doesn't come to you. Again, we're looking for the largest perfect square that is a factor of 80. I might start with 8 times 10. It's the first thing that pops into my head. That takes me to 4 times 2. 2 is prime, so we're done. And 4 has 2 and 2 as its products. 10, of course, is 2 times 5. Now, if I notice any pairs, then I'm well on my way to finding a perfect square. A pair of 2s means that it's divisible by 4, and it reminds me that 4 is a perfect square. Here's another pair, so it's divisible by 4 a second time. In other words, it's divisible by 4 times 4, which is 16. What's left over? The only prime I haven't touched yet is the 5, so 16 times 5, yeah, that gives me 80. All right, so here we've got 16 and 5. So we've got 5 root 5 for the first term minus 7 times 4 times the square root of 5 for the second term. To tidy up that second term somewhat, so we have negative 7 times 4. Those are both two regular numbers, neither under the radical sign, so that gives us negative 28 times the square root of 5. Turns out that we did have like radicals in the end after all, so now we can go ahead and add those. 5 minus 28 is negative 23, so we have negative 23 root 5 as our final answer.